Hello. So my topic today is about eigenvectors and singular vectors. If you are completely comfortable with this concept and you know that for the same matrix there might be a subset of eigenvectors and another set of singular vectors and they serve uh, uh, two different subsets of the matrix. In fact, eigenvectors are relatively immune to the effect of the matrix. The matrix just stretches them, it can't rotate them. And singular vectors for the same matrix are the most sensitive for its effect, especially those associated with the highest sigma. They are stretched the most and rotated the most. If you are completely comfortable with this, then congratulations. You can jump directly toward the visualization. I came up with a naive thought to visualize the effect of eigenvalue and singular eigenvalue and associated eigenvectors, and singular values and associated singular vectors for the same matrix using a drawing and color palette. If you are not completely comfortable with this concept and you, like me, coming from medical background, naively thought that singular vectors for rectangular matrix and eigenvectors for square matrix, then no, kindly bear with me throughout this introduction first. So I want to start by reviewing those basic concepts. The concept of eigenvector and eigenvalue. If x is an eigenvector for A, then A just stretches this vector by factor of lambda without it changing its direction, without rotation. And the concept of eigenvectors, or we need eigenvectors whenever we are speaking about the ultimate state of a system, like resonant frequencies, like steady state of Markov chain. Whenever we are speaking or want to see how our system will settle eventually, we go for eigenvectors. And it's true that only square matrices have eigenvectors, but square matrices can have both eigenvectors and singular vectors, okay? What is the difference between singular vector and eigenvector? First of all, from the equation, okay? Singular vectors aren't just stretched, okay? The direction of the vector multiplied by A had it changed its direction, and that's why we are denoting it by U. So it had been stretched by factor of sigma and rotated. What still preserved the inner product between the the singular vectors, okay, before they had been multiplied by A, and the singular vectors after they had been multiplied. Before and after, they should be orthonormal to each other. They are orthonormal before their multiplication, and they should stay orthonormal after their multiplication. And that's why we can write A with this factorization, singular value factorization or decomposition. Actually, it has another name or spectral theory for rectangular matrix, but it isn't exclusive for a rectangular matrix, and we will see this shortly. What does this represent? In physics, what does this represent? Or physically, what does this represent? V, especially V, is associated with the highest sigma, is a vector that had been subjected for the maximum change by this matrix. It had been stretched the most, changed the most, and also rotated. Singular values and eigenvalues can be the same for the same matrix if the matrix satisfies this property. Symmetric and positive definite, or positive semi-definite. Positive definite means all eigenvalues are positive. The determinant and subdeterminant all are positive, and it satisfies this property, okay? X multiplied by A multiplied by X transpose, this will be a number, okay? Is positive for all X, okay? A multiplied by X, this is a vector. Taking the inner product with X again, okay? This is a scalar. it would be positive for all x's. This is the meaning of positive definite. And this is the condition in which the eigenvalues equal the singular values, positive definite and symmetric. Still we are in the introduction, but I want to make sure that you are with me in the same page. So we will have an example for this matrix that has both eigenvectors and singular vectors. This matrix will be a shear matrix. Shear matrix keep the x component at its position 1, 0, okay? And just moves the y component or moves the y-axis to new direction. This is what shear matrix mean. So we calculated the eigenvalues and the eigenvectors using NumPy for sake of demonstration only, okay? And as expected, okay, the only vectors that will continue to fall in the same direction is the vectors that are in the x direction, okay? So the eigenvalue is 1, okay? Actually, and eigenvector, one eigenvector, which is 1, 0, okay? Only the vectors that are on x direction will continue to be in the x direction. Applying this matrix over our original grid, we will see this transformation. The eigenvector stayed on its place. The eigenvector stayed on its place. Other vectors had been rotated and stretched. The same shear matrix, okay, which is a square matrix, by the way, okay, for the same shear matrix, which is a square matrix, we will find the singular values and singular vectors. After running the program, okay, we have two singular values and corresponding to singular vectors, okay, and they have, this is for the same shear matrix that we had already done the eigenvectors. But they have different meaning. Singular vectors have very different meaning. Actually, this is the vector that had been, okay, stretched, and this is the other vector that had been squished, okay? And notice, if you had taken the dot product between them, okay, it will be equal to 0, because as I told you, singular vectors must be orthonormal to each other. Taking the dot product between them must be equal to 0. What will our matrix do to our two singular vectors? Okay, let's restart it. Those are our two singular vectors, and notice they are perpendicular to each other, and this is our starting point, okay? One is blue and one is red. We will find where this blue one will ultimately set and this red one will ultimately set. You see, it had been stretched and rotated, and the red one had been squished and rotated, okay? And still they are perpendicular to each other. Those new blue and the new red are the U, okay, in this singular value decomposition. Okay, done with the introduction, let's start the fun. So we have this colorful image of the brain, and we will distort it and try to reconstruct it using eigenvectors and singular vectors. You know that every image can be represented by a matrix, and this matrix can be retrieved using Python library. Not just retrieved, it can also localize where exactly in this matrix this brain is drawn, okay? Because as you see, most of the image is white, so most of the matrix is 250. And we will retrieve exactly where the brain is, the matrix that represents the brain, and then we will distort it and try to reconstruct it. Actually, I will try to show you the eigenvalue and singular or eigenvectors effect and singular vectors effect in the same image. And I think you will not forget it after this. This is the true not the true meaning, but simulation to the spectral theory. You know, spectral coming from like a prism, decomposing the white color into image, okay, into several colors. We are playing with the essence. Let's go quickly through the code just to make sure that we are in the same page. As I told you, there is built-in function in this library, okay, that facilitates this extraction of the matrix, okay? Not just the extraction of the matrix, but also localization of where we would like to work. So we just imported this library from which we converted our image, okay, into RGB, and then converted it into a matrix, okay? If I printed this matrix, you will find it full of 250, 250 everywhere, okay? So this is exactly where our brain exists, okay? And then we choose from our matrix only the data that is below, okay, 250, because you know 250 is the highest white color, okay? Anything below the 50, I would like to have it, okay, in my matrix. So this is how we had extracted our brain from this white lake. Okay, and this is our matrix, okay, of RGB. This is matrix of RGB that we will use to distort our brain, okay, and then we will try to reconstruct it, okay, using the concept of singular vectors and eigenvectors. It's a square matrix that has both eigenvectors and singular vectors, and they are different from each other, and we will see how, okay, shortly. As you see, we had this is our brain, okay? This is the extracted brain, okay? And this is its indices. This is the indices, okay, of this brain in the big matrix, and we will multiply this colorful this colorful brain with definite borders, okay, with this matrix, okay. Actually, we will multiply it several times to see the effect of eigenvectors, okay, because as we told before, the effect of eigenvectors appear in the steady state. So to see the effect of eigenvectors, we will multiply this matrix by this matrix that scramble the color with our structured brain, okay, and see what will happen after like 5 iteration. Okay, before going ahead and start, what do we expect? We have our RGB matrix, okay, scramble matrix or palette matrix, whatever, okay, and we can extract our eigenvalues and eigenvectors from it. We will focus on the biggest eigenvalue and its corresponding eigenvectors, okay, and its corresponding eigenvector, and we let the program do it for us. And here is the eigenvector, okay, and it, of course, a combination of color, okay, in RGB, and we would like to see what is the color, okay, to know how our brain, or to have like an intuition or I guess how our brain will end up, okay, after like 5 iteration. After running the code, this is our eigenvector. So we are expecting that after multiplying this matrix, okay, with our brain matrix, okay, 5 times, or after 5 iteration, our brain will turn into this color, okay, gradually. So let's see, let's try. This is our code, okay. As you see, we had 5 iteration, okay, 5 iteration of multiplication, and then we would like to see how our brain will look like. Voila. Well, yeah, it's all stained and actually lost its landmarks, right? There is 2 problems. It's all stained, okay, and lost all of its landmarks. There is also one thing I would like to make clear, okay? Throughout this frequent multiplication, okay, we had updated our current brain matrix. Okay, so each time we are updating our current brain. Okay, updating it and multiplying it, updating it and multiplying it. So we preserve it, okay, or saved our last matrix. Okay, our last matrix that gave us this pink color. Okay, but life can't continue to be pink. Okay, we would like to return back to our original well-defined brain. Okay, with prominent borders. Okay, we can't just subtract eigenvalues. Okay, here is how they differ from each other. We reach this state through eigenvectors. Okay, to return back to the definite well-defined, okay, state, okay, or our starting point. Okay, we can't use eigenvectors or eigenvalues. We will have to use singular vectors. Okay, but this time we will use the singular vectors of last matrix. Okay, this is not actually what I would like to show you in the same picture. Okay, but it's important. Okay, because as you noticed, okay, it's like an image. We added a lot of noise for it, and we would like to return back to the original. Okay, we reached this through the eigenvectors. Okay, and to return back to well-defined, okay, we need singular vectors. And still, as promised you, I will show you all in the same picture eventually. Okay, how to remove this pink veil. We will have singular value decomposition of our last matrix. Okay, the last matrix of this pink brain. We will decompose it through singular value decomposition. Okay, and we will take just the highest, okay, singular value and its corresponding singular vectors. Okay, this is the vector that had been stretched the most and rotated throughout this journey. Okay, we will take just the highest singular value with its associated v and u. Okay, and we will construct a matrix. Okay, actually this thing had confused me at first. Okay, this is an outer product. Okay, this is like a row. Okay, and this is all a column. This is column. Okay, and this is a row. So this is an outer product, and we will save this matrix. Okay, into this variable. Okay, first component. Okay, so up to now we had matrix, okay, of this pink colored brain. Okay, and we just factorized it through singular value decomposition. We had taken the maximum or the highest singular value and its associated singular vectors. This is an outer product, so the result is a matrix. We will keep it in the first component. Okay, and we will take this pink matrix, okay, pink brain matrix, and just subtract this matrix from it. Okay, and we will see the effect. Here is the effect. Okay, just in one step. Okay, all the other steps isn't math. It's about reconstruction or returning back from RGB to pixel and so on. Okay, so it's only in one step. We just removed the highest singular value and its corresponding singular vectors, and we had our brain again, not in the same colors. Okay, we had removed just one. Okay, the highest one. Okay, but we had its features at least again. And this is how they remove the noise, okay, from an image. Suppose like patient in CT or MRI, and he moved during the imaging. Okay, to subtract this effect. Okay, just in one mathematical step. Okay, and then all the other steps is just, as you see, built-in function to convert between numbers and the photos that we see. Okay, so back to our scramble matrix. Okay, we would like to see its eigenvectors and singular vectors. Okay, and the dynamics. Okay, with each iteration, how we reached this veal color, pink color, okay? So this is our original matrix, scramble matrix, okay? I'm speaking about scramble matrix right now, okay? And first we got the eigenvector of it, okay? And we had shown that this is the color of eigenvector, okay? What will happen if we factorize this matrix, okay, into its singular vectors, okay? And we would like to see the colors again. So no cheating or magic, okay? We just factorized the scramble matrix, okay, our small matrix, okay, into singular value, okay? And we had taken those vectors, okay? The V, okay? Actually, in the first time, I just tried to print one of them just to make sure that the code is working, okay? But then I printed them, not just printed them, okay? I converted them to color. And this is our V's, okay? And not just V's, okay? We will also get our U's, okay? So this is V after multiplication by M, we get this sigma U, okay? And this is V, and after multiplication with M, we get this sigma U, okay? And this is another V, and after multiplication with M, we get another sigma U, okay? You can see this color, okay? It seems like more composed of yellow, okay? And green, okay? It's something between yellow and green, okay? And I will show you, okay, the first colors, okay, to take the pink color, okay, are those yellow and green, okay? And then the others after several iteration, okay? But this is the true meaning of singular vectors, okay? This is a singular vector V that when multiplied, and this is the vector associated with the highest singular value, okay? Once it is multiplied by this matrix M, turn it into a pink color, okay? So this is the vector most sensitive to change, okay? Let's we see after several iteration. Yes, this is the one, okay? After several iteration, you can see the yellow color is the first one to take the pink color, okay? And then this blue color first turned it into green, and then the second one to take this pink color, okay? And then the others, okay, came. And you can see the dynamics, okay? How every color, okay? Especially the color that is formed by, okay? Combination of those will give us the first singular vector, okay? That's why the first singular vectors, as you recall, this is the most sensitive, okay? This is associated with the highest singular value. And that's why they are the first to take the pink color. This is the first, and this is second. And then the others came. To put all together, it's not with a very high artistic taste, but it shows, okay? This is the eigenvector color, okay? And this is the singular vectors color, okay? We had the matrix of this, no, we had the scramble matrix, okay? And we had this matrix, we factorized it into singular vectors, okay? And those singular vectors are those, okay? And this is V1, V2, V3, okay? And after multiplication by M, the scramble matrix, we have sigma U1, sigma U2, sigma U3, okay? And if you try to get its eigenvectors, okay, you have this color, okay? We get this color after 5 multiplication, okay? But what is the first color to change, okay? What is the thing that had first affected the yellow color, okay? And the blue color, because this color is actually a combination of yellow and blue, okay? So you can see the first one to turn yellow, from yellow to pink, and this is the second, okay? Not just this, okay? The red color also, okay? The red color, because it's mostly blue plus purple, okay? Turn it first to purple, okay? And from purple, convert it to green, okay? So the red color, because it has a lot of purple, okay? First convert it to purple, okay? And from purple, uh, like actually what our matrix predicted through singular value decomposition, it converted to green, okay? And then from the green, okay, to the pink. So this is the dynamics of our system, okay, throughout the journey, throughout the process, okay, and this is when it settled down, okay. I know we are twisting the meaning of spectral, okay, because either eigenvectors or singular vectors are mostly mentioned within the spectral theory, okay. We are twisting the meaning of spectral, but it's crystal clear, okay. The transformation with each step up to the steady state. I hope you had some fun, okay, and that's it.